Here's another question that is commonly asked in quant roles. The question goes, you're waiting for a bus at a bus station. The buses arrive at the station according to a Poisson process with an average arrival time of 10 minutes. If the buses have been running for a long time and you arrive at the bus station at a random time, what's your expected waiting time? On average, how many minutes ago did the last bus leave? So the question tests your understanding of Poisson process and especially the properties related to it. So in the next few slides, we'll see what a Poisson process is, what are its properties, and how do we approach this problem. So let's understand the problem once. The buses arrive according to a Poisson process with an average with a rate of lambda equals 0.1 per minute. The average inter-arrival time becomes 1 over lambda, which is 10 minutes. Now, if you're familiar with Poisson process, you'll know that the inter-arrival time is an exponential distribution. And for an exponential distribution with parameter lambda, the expected value is given by 1 over lambda. So our inter-arrival time becomes 1 over lambda equals 10 minutes. The process has been running for a long time, and we're given that we arrive at a random time. And two questions have been asked: the expected waiting time and how many minutes ago did the last bus leave. Let's briefly go through what a Poisson process is. So a Poisson process is a mathematical model for events that happen randomly, independently, and with a constant average rate over time. You can think of any uh, process such as the number of customers arriving in a store. This would be random, independent, and with a constant average rate over time. The number of calls received by a call center, the number of accidents happening on a highway. We usually denote the average rate by lambda. Always remember that lambda is always per unit time. So if we are given that lambda equals 5, this would be some unit time. So for example, lambda 5 here is per hour, means that on average 5 events are happening in 1 hour. We also have a formal mathematical definition for it, but the important thing to note here is the distribution for Poisson is given by this expression. This should be t here, probably that nt equals k equals lambda t to the power k times e to the power minus lambda divided by k factorial. Now, k is the number of events that are happening in a time interval of length t. So if we have a time interval of t and 1, 2, 3 events are happening, then k is equal to 3 and t would be whatever the length of this time interval is. Distribution of events. Number of events in time t. Nt is a Poisson distribution with parameter lambda t. Let's take an example. Coffee shop receives customers at lambda equals 3 per hour. What is the probability of receiving 5 customers in 2 hours? So immediately you should think of this as k and this as t from the previous equation which we just saw. So k is the number of events, t is the length of the time duration. And all you have to do is just plug these values into the PDF of a Poisson distribution and you will get the answer. Coming to the inter-arrival time, the time between events, let's say it's given by t1, t2, and t3 are IID exponential with parameter lambda. So if you're given a Poisson process with parameter lambda, the inter-arrival times are exponentially distributed. The PDF of an exponential distribution is this: lambda e to the power minus lambda t, and the expected value is given by 1 over lambda. This is an important property that is very commonly used in a number of different questions, and especially the properties that would follow from the fact that the inter-arrival times are exponential uh, is used in a number of different questions, including this question as we'll see in the next few slides. So if events are happening at a rate lambda equals 10 per minute, the average time between events would be 1 over lambda. It's 1 by 10 equals 6 seconds. One of the properties of the exponential distribution is the memorylessness property, which says that, considering the example of waiting for a bus at a bus station, if you have already waited for s time units with no arrival of a bus, your remaining wait time till the next bus is the same as you've just started. Mathematically, this is written by this expression over here, which is probably that t is greater than s plus t, given that t is greater than s, is equal to probably that t is greater than t. Now, you can evaluate this expression on the left side. by plugging it in the PDF of exponential distribution, and you'll be able to arrive at this right-hand side fairly easy. So this property is very commonly used in a number of different problems, and this is also the key to answering this question which we have here. So the expected waiting time until the next bus. If t is the time until the next bus from random arrival, we know from the previous slides that the Poisson process t, the inter-arrival time, is an exponential distribution with parameter lambda, mean 1 over lambda. So the expected value of inter-arrival time is given by 1 over lambda, which is 10 minutes. So the expected waiting time will be 10 minutes, regardless of how much have we already waited. The Poisson process has got another property called symmetry in addition to the memorylessness property. Now, if we assume that A is the time since the last bus, then using symmetry and memorylessness property, we are able to conclude that distribution of A is also exponential with mean lambda, 1 over lambda, which means that the expected value of A is also 10 minutes.